All right, it's already 10 and let's get started, okay? So we're gonna continue our discussion on the particulate matter. I have to say that PM is a major part of our class. So it's gonna, before the midterm, we're mainly going to deal with these particles and also a system to remove these particles, okay? So right now we're just getting some general informations on what are the properties of these particulate matter, okay? So we'll continue discussion on the size distributions. So last class we went through quite many equations on what are the size distributions, especially on the log normal size distributions. So let's do a quick recap. So last class we talked about the sources of PM. We mentioned that there are mainly two methods to form these PM, right? We can use the top-down method, which is breaking things apart, right? That happens when we do construction. And we also have the bottom-up approach. So this happens when we combust something, right? Or like the Smoky Mountain, right? So we have molecules getting together with each other and form these stable clusters. So we also mentioned the size distribution. So basically, people are maybe interested in a series of properties of particles. So last course, we just mentioned about people are interested in the size, interested in concentration, but actually people are also interested in the chemical composition, toxicity, so on and so forth, like mass, so on and so forth, right? But the quite important one is called the size distribution, which basically contains both the particle size and the concentration. So you remember when we make the plot of the log normal size distribution, right? So this contains both the size of the particle and also the mass concentration of the particle. That's why size distribution is a quite important item that we have to go through this class again. So regarding the measurement of the size distribution, we mentioned that we can use a cascade impactor. So cascade impactor is just a multi-stage impactor, right? So each stage of the impactor will collect particles of specific size. So for example, for this one, so particles of larger sizes will get collected by the stage 1, right? Remember, the potatoes will get collected on the first stage, right? Ping pong ball will get collected in the second stage, third stage, maybe the a grain of sand, right? The fourth stage, it can be something else. So then we have a question. So why can't we reverse the stages of the cascade impactor? Let's say we put the stage 4 at the top, stage 3, 2, and 1. So let's do a quick pool. To see why can't we do that? Five more seconds. Okay, we'll stop here. All right, so most of you guys are correct, right? So it is quite obvious. Basically, if we switch the fourth stage to the top, then we're gonna collect everything on the first stage, on the fourth stage, right? There's no way we can collect particles further below. And that's why we will not be able to differentiate particle sizes. So everything will just collect down here, right? That's why the stage sequence matters a lot. So actually, when you use a cascading impactor, actually I have some demonstrations of the cascading impactor in my lab. They will specifically label the stage number 1, 2, 3, 4, 5 for A, B, C, D, E, F, G, right? So you have to arrange those stages in order. Otherwise, you will just lose the size information. So after we have the size distribution, we mentioned that actually most of the PM in the atmosphere, they will follow log normal size distribution. People use these distributions quite a lot, right? So instead of using Gaussian, we decide to use log normal distribution on one hand because it fits the size distribution better, because when we plot the size distributions, so the x-axis will just goes according to the log scale, right? And normally the PM in the atmosphere, they will show size distribution looks like this, okay? And under this situation, we can just easily use a log normal size distribution to fit it, right? But on the other hand, the log normal distribution constrains that the dp have to be always larger than 0, because when we use Gaussian, then if it's in linear scale, let's say 1, 2, 3, 4, then it will have the scenario when dp is smaller than 0, right? So for this part, we just cannot explain it. So that's why we don't want to use the Gaussian, but instead use the log normal, because even if we go across the x scale, then it's just going to be 0.01, right? 0.001. It's never going to reach to 0. Okay, so once we know the size, log normal size distribution, finally we mention something related to the cumulative size distribution. Right, the cumulative size distribution just shows the fractions of particles below certain sizes. Just shows the fraction of the particle below certain sizes, right? So for example, if we still plot it in the log scale, right, it's going to show something like this. Right, at the maximum size, the cumulative fraction would be 100%. Well, at the smallest size, a cumulative fraction will be almost 0, right? And because the size distribution have a shape like this, since we're adding them up together, right? So it's going to grow faster at the near to the peak, or near to the peak size of the distribution. So it's going to show like this. So then we may have a question, because for a lot of actual applications, we will try to, let's say, we need to try to see whether a size distribution follows log normal distribution. Of course, we can do the cascade impactor measurement. Let's say we measure M1, M2, M3, M4, so on and so forth, right? Of course, we can plot these mass in a plot that looks like this, and use a curve fit to see whether it follows log normal or not. But there are actually easier ways to confirm whether a size distribution follows log normal, okay? How to confirm a size distribution follow log normal. So there's an easier way in engineering to confirm this, okay? So for example, let's look at this problem here. So the following data obtained from a cascade impactor, okay? Since we already introduced that, so basically, cascade impactor is a particle sampling device that classifies particles by size, right? So it wants us to show that the size distribution, or the information here below, so it shows that the size distribution is log normal, and it wants us to find the dp d50, which is the particle size that has a cumulative fraction of 50%, and the sigma g, which is a standard geometric standard deviation. Okay, so this is the information it provides us. So based on the properties or functionalities of the cascade impactor, basically tell us what is the mass of the particles in certain size range, right? For example, 0 to 2 micron, the mass is 4.5, 0 to 5 has this value. So different stage will give us different mass, right? Finally, above 25 micrometer, we have this mass. So if we correspond to an actual impactor, then this is going to be stage 1, right? Stage 1 has a cut size of 25 micron. So all the particles above 25 micron are going to get collected here, and we can measure its size. So the second stage has a cut size of 15 micron. So that's why here we can measure its mass. That's going to be 15 to 25, right? So on and so forth. So we can get all of these information. So finally, for 0 to 2, of course, we cannot find a stage that has a cut size of 0. So the way we measure that is by letting the remaining particles go through a filter. So the filter will collect all the particles that remains, right? So this will give us the mass for the smallest particles. So now it wants us to confirm that this size distribution follows a log normal size distribution. And it is quite challenging if we just plot it in this way, right? It's difficult to tell. So the way we do it is to confirm it with the cumulative fraction. So we're going to first calculate what is the cumulative fraction of particles below 2, below 5, below 9, all the way below 25, okay? So the way we do that is first, let's say we list out the cascade impactor stages, 0 to 2, 2 to 5, 5 to 9, 9 to 15, 15 to 25, and above 25. So we can list out what is the mass. And we have 4.5. I'll just copy all of these numbers here. Okay. So with this mass information, we can first calculate what is the fraction of the mass that's within this single bin here. So the way we do that is we can divide these numbers by 920, which is the total mass. Okay. So if you do the calculation, basically, this is going to be the value you have. Okay. Divide by 920. Okay. Then we need to calculate a cumulative mass fraction. So the cumulative mass fraction is just the mass fraction of particles below certain size, right? For example, below 2 microns, that's just going to be this value, okay? So the percentage is going to be 0.49%. So here on the textbook, it's just rounded to 0.5%, okay? And then the cumulative mass fraction of particles below 5 microns are just going to be these two values added up together, right? These two add together, you have 20%. Okay. So the cumulative mass fraction of particles below 9 microns are going to be these three adding up together, 60%. So 90%, 98, until 100%. Okay. So once we get the cumulative mass fraction, we can use a plot called the semi-log plot. So here I'm showing the plot here. Maybe it's a little bit, let's just zoom out a little bit. Okay. So this is the an engineering plot that people use a lot to tell whether size distribution is log normal or not. Okay. So on the x-axis, it's a cumulative fraction of particles below certain size. And on the y-axis is the particle size, okay? So what we're going to do is we'll just plot the data points. Let's say the cumulative mass fraction of particles below 2 is 0.5. So we're just gonna add a point corresponding to 2 micrometer and then find out the 0.5, okay? So 0.5 is going to be somewhere, let's say here, okay? This is the percentage, it's fraction, right? 2 micron correspond to this point. So let's do the remaining data points. I'll just first copy the numbers here. 5 micron, you have 20, 9, you have 60, 15, you have 90, 25, you have 98. Okay. So let's plot the remaining points. At 5 microns, we need to find 20%, which is here, right? And then 9 microns, we have 60%. 15 micron, that's somewhere here, right? We have we have 90%. And then at 25, we have 98. Okay. So now, so the engineering plot or semi-log plot makes sure that if it's a log normal size distribution, it's going to follow a straight line. Okay, it is almost very close to a straight line here. So that's why it is a log normal size distribution. Okay, so if you look at further take a look at the semi-log plot, it is a little bit different from the most commonly used semi-log plots. Okay, so on the y-axis is still log normal scale, right? You have 1 to 10, 10 to 100. They have the same gap here, right? But on the x-axis, for the fraction, it's not in linear scale, right? So you see that the fraction that's close to the fraction that are close to 50%, they're more crowded. But the fractions that are very small or very large, they're stretched, right? So this kind of makes sense because theoretically, if this scale is linear, it's gonna look like this plot, right? If it's linear scale in the fraction, then it's not going to show a straight line here, right? So we may have a question, so why is this plot so magical, right? So this have to deal with so basically these are the data points again, right? So it has to deal with because of the properties of these log normal size distributions. So so last class we showed that actually the log normal size distribution follows the equation of m total divided by square root of 2 pi dp sigma g forgot a log here. Okay, log dp minus log dpg divided by 2 log of sigma g squared. So last class we showed that the log normal size distribution are going to follow an equation that looks like this. Okay, and so basically in this equation we mentioned that the sigma g is the geometric standard deviation. And the dpg is called the geometric mean. Okay. So for log normal size distribution, if we calculate its cumulative fraction, so we should know how the cumulative fraction works, right? So it's just an integral, let's say 0 to let's say this way. So this is how we calculate the cumulative mass fraction, right? So basically, it's according to the definition, right? So we have to integrate the area that's below the size distribution and divide that by the total area or the total mass. So the total area will be mass total, right? And then we just need to calculate what is the mass that's below this certain size. This is how we should calculate the cumulative fraction. So if you plug in this equation to the integral, so I will just skip it for this class. If you want to know more, again, go to your cumulative calculus class. Okay. So the final solution for this equation is actually this. So it's 1/2, 1 plus error function log dp dpg divided by square root of okay. So the final solution looks like this. Okay, it is a little bit scary, I would say, because we're dealing with another function that we're not quite familiar with. Okay, so this is called the error function. So the error function, you can just regard it as like a symbol. Okay, so it's similar to, let's say, exponential or log. Okay, so it's just a way of representing a calculation process. Okay. So now you can see that the cumulative mass fraction depends on 3 parameters. So it depends on the size we're interested in, right? Let's say if we want to calculate the cumulative mass fraction up to 10 microns, then this capital DP will just be 10 microns, right? So this is the size that we're interested in. So it depends on the geometric standard deviation. It also depends on the geometric mean. It also depends on the geometric standard deviation. So it depends on these 3 values here. But one thing we can know for sure is that it is quite special under 3 conditions. Okay. For example, when dp, should use capital D here. When dp is equal to dpg, then we know that the log term will become log 1, right? So basically this cumulative fraction will become 1/2, 1 plus our function of log 1 divided by something in the denominator, right? So log 1 is equal to 0, and error function of 0 equals to 0. So that's going to be 50%. Okay, so what this means is that when the size of interest we're interested in, size of interest is equal to the geometric mean, then the cumulative fraction will be 50%. So what does that mean? It just means that, let's say, if we go back to the size distributions, so the middle point or the axis of symmetry will correspond to the size of dpg. So on the left-hand side, the mass fraction is 50%. On the right-hand side, the mass fraction is 50%. Okay, so this is a special size. When the particle size is equal to the geometric mean, then basically the mass fraction before that, the mass fraction after that are going to be equal, which are 50%. Okay, so when dp equal to dpg, we have 50%. So the other point of interest is when dp is equal to dpg multiplied by sigma g. So if we plug in this term into the calculation, so you can see that on the g, sigma g will be equal to 1 plus error function of log sigma g. Okay, if we plug in this dp into this equation here, and then on the denominator we have a square root of 2 log sigma g. Okay, so these two things will cancel out. So we're going to get a constant value here. All right, that's 84.1%. So this will apply for all log normal size distributions. So if we log normal distribution, then if the size is equal to the geometric mean multiplied by geometric standard deviation, then the cumulative mass fraction will always be 84.1%. All right. So if similarly, if the particle size that we're interested in is equal to dpg divided by sigma g, we can do the similar thing. So dpg divided by sigma g, 2 1 plus our function log 1 divided by sigma g. So we know that log of 1 over something is just negative of that term, right? So we have negative log sigma g. So again, these two will cancel out, right? We just have 1 plus error function of negative 1 over square root of 2. So this is going to have a value of 15.9%. Okay. So these are the properties of the log normal size distribution. So basically, if we have 3 different sizes, so it just applies for all different types of log normal size distribution. We always have the mass fraction when the particle size is equal to dpg, the cumulative mass fraction is 50%. When it's equal to dpg multiplied by sigma g, the mass fraction will be 84.1. And when dp is equal to dpg divided by sigma g, the mass fraction is 15.9. Okay. So again, let's say if we go back to I think originally we were trying to discuss why this is a case, right? So why it's going to follow a straight line here. So if you recall, when we plot out the cumulative mass fraction, we had something like this. Okay, so basically what happens is for the log normal plot, we just switch the x-axis and y-axis first. Let's say this is what we get. Then we know it's going to be something that looks like this. So we have 100% here, right? And then around 0 here. Okay, so if you compare, so this is when the cumulative mass fraction is in the linear scale. So now you see what this plot does is it basically stretch out the region here and here. Okay, it stretches the fraction when it's getting close to 100%, and also stretches the fraction when it's getting close to 0%. So by stretching that, we can get a linear plot. Okay, so this is what this engineering plot did, right? So we stretch out the region where the fraction is the largest, and also stretch out the region when it's the smallest. So that's why we get this plot here. So if you're interested, actually this stretching has to follow the error function that we discussed earlier. Okay. So I have a few backup slides at the end of this class note. If you're interested in that, you can see actually how they generate this plot, and actually applies for all different types of log normal distribution. For example, if a log normal distribution looks like this, right? If a distribution looks like this, it's also a log normal. If it looks like this, it's also a log normal distribution. So it's the parameters we discussed. What are the dpg, or what are the sigma g? Okay. So now let's get back to this problem here. So it wants us to first confirm the size distribution is log normal. We have done that, right? It is it's linear. It shows a straight line in this semi-log plot. So that's why it is log normal. But it also wants us to find d50 which is the size that has 50% of the cumulative mass fraction, okay? And also sigma g. So now if we want to look for this point, 50%, what should it be? Right? It should just be the point that has 50% of the cumulative mass fraction, and we can trace that. That's somewhere around, let's say, 8.2 micrometer. Okay, so this is D50, and this is also DPG, right? We mentioned when the particle size is equal to geometric mean, then the mass fraction, cumulative mass fraction is 50%, right? So now we just need to solve for sigma g. So how do we do that? So if you recall, here we introduced that when particle size is equal to dpg multiplied by sigma g, we have 84.1. When particle size is equal to dpg divided by sigma g, we have 15.9, right? We can just look at these two data points. So when at 84.1, that's somewhere here. Right? And at 14.9, somewhere here. Okay, so now we know that dpg multiplied by sigma g is equal to, let's say this is 15, okay? And then dpg divided by sigma g is going to be equal to 4.5, okay? So now we have this relationship. And then we can again solve for dpg if we multiply these two equations together. So dpg squared is going to be equal to 15 multiplied by 4.5. And sigma g is just these two equations dividing each other, 15 divided by 4.5. Okay, so by using this plot, we can solve for these parameters. So you may wonder, does this number match with this number? So we have to do the calculation. So if they theoretically they should be exactly the same, but normally when we use this plot to identify the data points, they may differ by a little bit. So we can just calculate in this way and then take the average. Okay, so that's going to be more accurate. But based on this equation, we can calculate what is the sigma g. So this is all by just using this simple semi-log plot. Basically, we can get a lot of information out of it. All right. So any questions until now? Good? Okay, nice. So let's do another practice. All right. So let's say we have a particle size distribution that is log normal. So it has a D50 or the DPG of 6 microns. Okay, and a sigma g of 2. So this time we know that this is a log normal size distribution. Okay, so it wants us to plot the distribution and then also determine the mass fraction of particles below 2 microns. So if we don't have this semi-log plot, so the typical way is we'll just plug in these 6 and 2 into this equation, into the size distribution, let's say, and then make the plot. But that's going to be very complicated. The semi-log plot helps us solve quite many things, okay? So the way we do that is first, so D50 is 6 microns. So let's just look at 6, okay? So that's going to be this point, right? And we have D50 and also sigma g. So we know that when dp is equal to dpg multiplied by sigma g, which is 12, the cumulative fraction is 84.1%. Okay, when dp is equal to dpg divided by sigma g, which is 3, the cumulative fraction should be 15.9%. So the way we do that is, let's look for 12. 12 is somewhere here. Okay, let's look for the 3 first. 3 is somewhere here, right? And we'll look for 14.9%, which is somewhere here. And then for the DPG equal to 12, that's equal to 84.1, which should be somewhere here. Okay. So then we can just draw a straight line because we already know that it is a log normal size distribution. Okay. So now how do we determine the mass percent of particles below 2 microns? We'll just use this line, right? This is 2 microns. Look for here. Vertical line, right? That's somewhere around, this is probably around 5.5%. Okay. So by using this plot, it really simplifies a lot of things, right? So we don't need to go through those very complex calculations. We just need to make a few data points, and then we can easily do easily calculate the mass fractions. For example, let's say now we're interested in the cumulative fraction below 4 microns. All right, below 4 microns, again, look for the data point here, right? That's around 30%. Right. So I hope this is clear enough. You also get a few practices in your homework problems. Okay, so let's try to get familiarized with this semi-log plot. It's going to be very helpful when we try to look for the size distributions. But let me know if you have any questions or if you are not clear on anything. All right. At the end of this class, I think basically I also want to go through the calculation of the particle removal efficiency. So basically, in this class, we're going to talk a lot about, let's say, PM control or the gas pollutant control, right? Let's say the pollution control methods. Okay, so people will always discuss something about, for example, the removal efficiency or control efficiency. So this efficiency just means the parts or the, let's say, the quantity removed divided by the total quantity. Okay, so this is how we calculate the removal efficiency. So if the removal efficiency is 100%, then the quantity removed is going to be equal to the total quantity, right? So let's say we have this example here. Let's say we have 300 spherical particles, but these 300 particles have different sizes. So 100 of them are 1 microns. 100 of them are 10 microns, and 100 of them are 100 microns. Okay, so they have different sizes. So let's say we have a device, we have a control device that is 10% efficient for the 1 micron particles, 50% efficient for the 10 microns, and 99% efficient for the 100 micron particles. And actually, this is a typical situation for a lot of particle removal devices. They're very efficient for removing very large particles, but they're less efficient when we talk about smaller particles. And this is also the reason why we have a lot of PM 2.5, right? PM 10, PM 2.5, mainly because these control devices, they're not efficient when they're removing these smaller particles, okay? So let's further assume that all the particles have the same density, and the 1 micron particles have the unit mass. This is just meaning that the density is equal to the density of water, which is 1,000 kilogram per meter cube. So it wants us to calculate what is number efficiency and the mass removal efficiency for the device. Okay. So people will also use these different values of efficiencies. So right now, let's say for power plants, when they're removing PM, they're mainly referring to the mass efficiency. Okay, so we'll find out actually how that's different in terms of different quantities. Let's say regarding the number efficiency, we know that, so we know the total quantity is 300, okay, by using this equation, 300. So the quantity removed for the 1 micrometer particle, so that's 10%, which is 10 particles, right? For the 100 particle, for the 10 micrometer particle, 50% is removed. So this should be 30, not 10. Okay, 30, and this is no, it should be 10. So we're just talking about this 100 micron particles, right? So that's going to be 100 multiplied by 10%, 100 multiplied by 50%, and 100 multiplied by 99%. Okay, so this is the number removal efficiency. Right, so if you do the calculation, I think I have the answer here. Do the calculation, that's going to be around 53%. Okay, so this is the number removal efficiency. And in terms of mass removal efficiency, then we need to use a different quantity, right? So the total quantity is going to be the total mass of all of these particles, right? So let's say this is number efficiency, this is mass efficiency, then this is going to be 100 multiplied by 1 micrometer particle. We know, let's assume that the 1 micrometer particle have a mass of A, right? So we know that the mass scales with volume, and the volume is the 10 to the third, or let's say 10 to the third of the diameter, right? So basically, for the 10 micrometer particle, the mass of those particles will be 1000 A, right? Because let's say volume is pi over 6 dp to the third. Okay, it's a cube of the particle diameter. So if the 1 micrometer particle have a mass of A, then 10 micrometer particle will have a mass of 1000 A, right? And then the 100 micrometer particles will have a mass of 10 to the 6 of A, right? So then the total quantity being removed are just 100 multiplied by A, 100 multiplied by 1000 A, and 100 multiplied by 10 to the 6 of A. So this is the total quantity. And the quantity removed is basically 100 multiplied by A multiplied by 10%, 100 multiplied by 1000 A multiplied by 50%, and 99%. So now you can see that basically this number in numerator and denominator are just largely determined by this value here. Okay, because all the A will just cancel out. It doesn't matter what is the mass for the it is for the 1 micrometer particles. They're all canceled out. So the number here is largely determined by this larger sizes or the larger particles. So if you plug in all of these numbers, you'll find out that the removal efficiency in terms of the mass is 99%. Okay, mainly because these numbers are too small. This is 10 to the 6. It's much, much larger than these numbers, right? So finally, if we do the approximation, it's just going to be similar to this value, and we have 99% here. Okay. So now you can see how different it is when we talk about the removal efficiency. If it's number efficiency, then it's 53%. If it's mass efficiency, that's 99%. what happens is we are generating a lot of PM 2.5 from this process, right? So basically, a lot of the particles are below 10 micrometer or PM10. A lot of them are not even removed in terms of PM1, right? So that's why, although a lot of PM control devices right now, they're stating that they have even have 99.9% remove efficiency. But if we talk about those particles that have the most negative effects on human health, so those devices are still not efficient in removing them, right? So just pay attention when we talk about either number efficiency or mass efficiency, because they will differ by quite a lot if we talk about particles with different sizes. All right. So that's all for the contents of this class. We don't have class for the upcoming Monday because of the Labor Day holiday. And so on Wednesday, I'll briefly introduce the term projects we're going to work on. So by that time, you'll also have your team assigned, so you can get in contact with your teammates, and we can start from there. All right. Okay. Thank you.